Hi class, today we are moving on in our look at intersections in R3, and we're looking at the intersection of three planes. Okay, I gotta be honest with you, this is actually one of my favorite notes ever. I just love how there are 8 different possibilities for how 3 planes can intersect. It's so cool. So I would encourage you to just stop and think about it for a second. If you have 3 planes, what are the different ways they can intersect? There are 8 of them. I think it would be a cool little challenge if you could figure out how many of the 8 you can come up with. I know you see 2 right there. But there are 4 ways that there is actually a solution to the intersection. So we call that a consistent system. And there are 4 ways that are inconsistent, so ways that we can't conclusively find one type of intersection. So while you're thinking about it, you can have points of intersection, lines of intersection, or planes of intersection. So you can think about that, see what you come up with. Or, just watch the video blindly. Do what I tell you to. That's always fun too. Anyway, so 3 planes are represented algebraically by a system of 3 equations with 3 unknowns, which is what we've been solving. So systems can be consistent, so one or infinite solutions, or inconsistent, there's no solution. So these are the 4 ways that we can have a consistent system. Just my pen here. So it's going to take you guys a lot of practice looking at the normals to help you figure out which of these it could be. So intersecting at one point would be if these planes, are kind of all coming in at different angles and just intersect at one point. So in this case, these planes are not parallel at all. So we would say that normal 1 is not equal to the scalar multiple of normal 2. And not equal to a different scalar multiple of normal 3, okay? So basically the normals are not related at all. They're not scalar multiples. Now we can also have a situation where, so this has one solution. We can also have a situation where it kind of looks like a book, like they all intersect along a line. So in this case, none of the scalars are scalar multiples. Sorry, none of the normals are scalar multiples here either. But here we do say there are infinite solutions because every point along this line is a solution and there's infinite points along a line. So that's why that makes sense. Okay, the next option is that 2 planes are coincident. So plane 1 and plane 2 are coincident and a third plane intersects on the line. So in this case, 2 of the normals would be scalar multiples, but not the third. Okay, so in fact, 2 of the planes are scalar multiples. So the entire equation of one plane would be equal to some kind of scalar times the entire equation of the second plane. So not only are the scalar multiples the same, but the entire equation has to be a scalar multiple. Sorry, not only are the normals scalar multiples, but the constant is as well. Okay, if just the normals are scalar multiples, but the constant isn't, what does that mean? Well, that means that the planes are parallel. But in this case, they would have to be coincident. Okay, and then the last consistent system, if there is a plane of intersection, because all 3 planes are coincident. So, of course, the normals will be scalar multiples. But we should also remark here as well that the entire equations of the planes will be scalar multiples. Okay, including the constant. All right, so let's look at some systems and use elementary operations to find out how this works. So you always want to check the normals before you actually go to try to solve a system, because you might be able to make conclusions without even having to do any elimination here. So I'm going to call this plane 1, 2, and 3. Okay, so check the normals. So here's 1 to 2, but this isn't the same ratio, so there's no ratio there. Then 1 to 3, and then nope, those aren't okay. And then 2 to 3, no. So you can see that no normals are scalar multiples. Okay, so if we're just considering consistent systems, the 4 above, then we know that this is either case 1 or 2 from above. So either they intersect along a common line or they intersect at one point. So I'm going to actually try to solve this system to figure that out. Okay, so I'm going to multiply equation 1 by -2. Okay, to get -2x plus 2y minus 2z equals +4. And I'm going to add that to equation 2, which is 2x minus y minus 2z equals -9. Okay, and this leaves me with y minus 4z equals -5. Okay, and we will call that equation 4. Okay, and I'll just change color just so it's kind of separate here in your mind. Now I'm going to multiply equation 1 by -3 so that I can add it to equation 3 and eliminate x there as well. Okay, so you get minus 3x plus 3y minus 3z equals 6. Add it to equation 3. So fun, right? Have you guys done a million of these yet? Are you just loving solving these? Okay. So 4y minus 4z equals 4. So I'm going to actually scale that to y minus z equals 1. And I'm going to call that equation 5. Okay, so now I can multiply, actually I can just multiply equation, okay, I'm going to go over here now. From here, I'm going to go over here. Okay, now I'm going to multiply equation 1 by -1, sorry, equation 4 by -1. So minus y plus 4z equals 5, and then add that to equation 5, which is y minus z equals 1. So the y's eliminate, and you get 3z equals 6. So z is equal to 2. That looks like z is equal to z. Hopefully you guys can. Z is equal to 2. Okay, so then you use back substitution and you find that y is equal to 3 and x is equal to -1. Okay, so we can conclude, because we were able to go through and actually find a unique point, we can conclude that these 3 lines intersect at the point -1, 3, 2. Okay. So now let's take a look at what it looks like when they intersect along a line. So this is going to be case number 2. So again, the first thing that we do, it's very important that you get in the habit of checking the normals. So I call this equation 1, 2, 3. So you check the normals first, and you'll see here there's no scalar multiples. So we're in case 1 or 2 again, assuming that it's consistent, okay, because we haven't gone over the inconsistent stuff yet. All right, so watch what happens. So I'm going to tell you right away, this is going to intersect along a line. Okay, so copy. Okay, I'm back. More pep in my step. Okay, I'm going to tell you right away they're going to intersect along a line. So let's see what's going to be different than before. There has to be something different, or else we would find a point, just like example 1. So I'm going to go ahead and try to solve this. So I'm going to multiply, equate. So I'm going to shorten these steps for you a bit. Hopefully you can handle it. So what happens when I multiply equation 1 by -1? And then I add it to 2. Okay, so I'm just going to show the result instead of the whole multiplication and stuff. When I do that, I get minus 7y plus 5z equals 3, okay? And then I would call that equation 4. Okay, then I would multiply equation 1 by minus 2/3 and add it to equation 3 to eliminate x in equation 3, and I would get minus 7/3 y plus 5/3 z equals 1, and I get equation 5. Okay, and if I want to scale this, because I don't like those fractions, because who does, I'm going to multiply equation 5 by 3 to get rid of them. So then I would get minus 7y plus 5z equals 3. Wah, wah, wah. Okay, so my new system at this point is 1, because that's what I used to eliminate the other two. 4, I didn't change it. And then 6, because I scaled 5 to get to 6, right? So check out my new system, 1, 4, and 6. What do you notice? Well, you should notice that 4 equals 6. So note now, okay, I'm going over here, that equation 4, the entire thing, equals equation 6. Okay, this means that there are infinite solutions. And that means that it has to be a line of intersection. Okay, so the question is, so that's how you identify that you're in that case. So now the question is, how do we actually find the line of intersection? Well, we're going to find the line of intersection of two planes like we did before in the intersection of two planes. So, I'll write that just so you have it in your notes. So now solve for line of intersection as we did before. Okay, so we're going to say remember we introduced a parameter, so we're going to say let z equals t in equation 4. So you get negative 7y plus 5t equals 3. So if you isolate y, you get 5 over 7t minus 3 over 7. Okay, so now we're going to put that back into equation 1 because we're looking for, since 4 and 6 are the same plane, we're looking for the intersection between 4 and 1. So now we're going to put that into 1. So we get 3x plus 2 bracket 5 over 7t minus 3 over 7 and bracket minus z equals 0. Okay, sorry, not minus z, minus t, because we let z be equal to t. Okay, and if we rearrange that and solve, we get x is equal to minus 1 over 7t plus 2 over 7. Okay, you can try that yourself. That's what you get when you isolate x. So that means that our line, those are the parametric equations of our line. Okay, this one, and this one. So if I wanted to write the vector equation, it would be 2 over 7 is the coordinate here, and then negative 3 over 7 is the coordinate there, and then 0 is the z coordinate, and I would be adding t, our parameter, and then my direction vector is minus 1 over 7, 5 over 7, and 1. But I can scale my direction vector. I can't scale this point, so it has to stay as that annoying fraction because that's a point on the line, but I can scale this to 1, negative 5, negative 7. T is in a set of all real numbers. Okay, so that is how you find a line of intersection. Finally, example 3. First thing, we want to check the normals, as always. So notice that if we look at equation 1, equation 2, and equation 3, so 2 to 4, that's a multiple of 2, but that doesn't hold here. 2 to 8, that's a multiple of 4, that doesn't hold. But 4 to 8 is a multiple of 2. Minus 1 to minus 2 is a multiple of 2 here. So the entire equation 3 is just equal to 2 times equation 2. So notice it's not just the normals, it's the constant as well. If it was just the normals and not the constants, then they would be parallel, but it is the constants as well, so these are coincident planes. So therefore they are coincident planes. So therefore we're in case, from the other one, case number 3. Because the first is not coincident with the other two. It's not a scalar multiple. So therefore, there will be a line of intersection. So we can actually solve for that line of intersection. So basically, this is just as before. You either find the intersection between 1 and 2 or 1 and 3, because 2 and 3 are coincident planes. So you go ahead and do that. So you can use 1 and 2, or 1 and 3. See, why do I do stuff like that? I put this and sign here, and then I write and there. Weird. Okay, so I'm just going to do 1 and 2. So if you take equation 1 and multiply it by -1, and then you add it to equation 2, I'm just going faster through the steps here. You get -3y minus 3z equals 3. And then you can scale that to minus y minus z equals 1. Okay, so now you can introduce a parameter. Let z equal t. So -y minus t equals 1. And so you can rearrange for y. You get y equals 1. Oh, I made a mistake there. Anyways, I made a mistake previous. -1 minus t. Okay, so there you have your y value. And then you can sub that back into 1. So you get 2x minus 1 minus t. I made a mistake on my notes, so I hope I can fix it properly. Plus t equals 1. So you get the t's cancel out and the 1's cancel out. So you actually get x is equal to 0, which is fine. There's nothing wrong with that. So therefore we get x equals 0 and y equals this and z equals t. So the line is equal to 0, -1, 0, plus t, 0, -1, 1, where t is in the set of all real numbers. And that is the line of intersection. All right, so let's get now into inconsistent systems. So these are 4 cases where there is no solution that we're able to find. And there's 4 ways for this to happen. Okay, either we have a triangular prism. So you can see my amazing diagram of that right here. So here's a plane, the blue one in the front, and then a green one and the blue one. So there's actually 3 different lines of intersection. And actually all 3 of those lines are parallel, which is interesting if this happens. But the normals of the planes are not. Okay, so that's one way for there to be an inconsistent system, a triangular prism. Now, another way is that there's 2 parallel planes, and then they intersect a 3rd plane. So here there would be 2 lines of intersection, 2 LOIs. Okay, so notice that normal 2 would be equal to some kind of scalar multiple of normal 3, but not the other normal. Okay, so there was a consistent system where this is the case. Okay. So if you go back to case 3 from before, here we had 2 normals the same. 2 normals as scalar multiples, but not the 3rd. What's the difference? Well, in case 3 of consistent, the entire equations were scalar multiples, okay, because they're coincident planes. Here, just the normals are scalar multiples and the constant isn't, because it is they're parallel, not coincident. So that's the analysis we have to look at and think about when we're making our decisions about what case we're on. Okay, the next option is 3 parallel planes. So notice here that all 3 of these normals will be scalar multiples. However, none of the constants will be. This is what's really important to understand, but no constants. Okay, so they will be all parallel, but none of them coincident. Finally, the last option is if you have 2 planes that are coincident. So like this is plane 1 and plane 2, and then this is plane 3. So 2 planes that are coincident, and then the last one is parallel. So there's no intersection here as well. This is an inconsistent system. So here, all the normals are scalar multiples as well. But what's different here is that 2 of the constants will also be scalar multiples, but not the third. So really, you just got to keep your thinking hat on and be able to analyze the normals and any scalar multiples and think about what that really means, determine what the possibilities for the cases are, and then get her done. Okay, so what happens here? So let's always analyze the normals first. So notice that there is no normal or coincident planes here. Okay, so there's no normal or coincident planes. Okay, so when that happens, there's actually only 3 different opportunities or 3 different options that it could be. So either they are from the consistent solutions, either case number 1 or number 2. So either there's a point of intersection or a line of intersection, or it's a triangular prism. That's what it's gonna be. Spoiler alert. Okay. So how do we find this? So we're like, okay, let's go and try to find the point or the line of intersection. And you go about your merry way. You multiply equation 1 by -1, and you add it to 2, and you get 2y plus z equals 1. You're feeling all good. Then you multiply it. You do the same thing again, and you add it to 3. And you get -4y minus 2z equals 0. And you're like, sweet, now I get to solve this system. So you multiply -1/2 times equation 5 to get 2y plus z equals 0 to get equation 6, because you can scale 5 to get 6. Now, check out 4 and 6. What do you notice? Okay, note the inconsistency. Okay, if you try to solve this, so -1 times equation 4 plus 6, what happens? You would get 0y plus 0z equals -1. Okay, there are no solutions to this. So that means that this has to be a triangular prism. Okay, it can't be a line of intersection or a point of intersection. Okay, so just to be really clear with you guys, if you have found that there are no normal or coincident planes, there's only 3 different options for you: point of intersection, line of intersection, or triangular prism. So basically what your strategy is that you go through and try to assume there's a point of intersection and go through and try to solve for it. So either you'll be able to go all the way through and find the point, good, great, if that's the point of intersection, or you'll hit a snag along the way. If the snag is that you get 0 plus 0 equals 0, then that means there are infinite solutions, which means it's a line of intersection, and you can find it as we did in example 2. If you get the case where you have 0 plus 0 equals a number, that is an inconsistent system because there are no solutions, and you can conclude that they're a triangular prism. So if there's no normal or coincident planes, those are your three options for solving. Other than that, really, it's about looking at if there are parallel or coincident planes, and then using your noggin to figure out which one it is. So for instance, in this case, notice here that these guys are parallel, okay, not coincident. Okay, they have the same normal, but different constants. So you know that they are parallel planes and not coincident, which tells you right away that there's no solution. As soon as you have any kind of parallel planes, there's no solution, okay? So that's the kind of analysis you're going to be doing. All right, guys, there's one of my favorite notes ever. I hope you enjoyed it as much as I did. Thanks for watching. I hope you learned lots.